Welcome to the online MOOC course in software engineering. In this lecture, we'll look into software maintenance models and how it is going to relate with cost forecasting. So the agenda for today is maintenance landscape, followed by the process models of software maintenance, the cost drivers associated, the estimation toolkit, and the budget with respect to the software maintenance. So the maintenance landscape. So we have learned about the software engineering life cycle, wherein maintenance comes as the last phase. Here we have already seen that maintenance will actually acquire the enormous amount of budget, which is more or less equal to 90%. Okay, so the 90% of the cost that is associated with the software is associated with the software maintenance. So if your requirements and the design, implementation and testing is very good, this maintenance will also be easier. But in case if we have done a little mistake in any of the prior phases, maintenance will become a very major problem. So that is what we have to learn in this lecture. So the maintenance consumes the majority of any software budget. Okay. So as I said, it is almost approximately 90% of the entire budget that is associated, and it is very important to make sure the planning with respect to the software so that we have the financial stability. So this maintenance is trying to provide a secure funding. It is trying to provide justification for long term budgets with data, and also helps in preventing the rewrites. Rewrites are normally costly. So what we mean by rewriting here is we are trying to do a particular functionality or a set of functionality over again. Okay. So which is actually costly because we are doing it for the second or third time, and it is also an unexpected overhaul with respect to the cost. The third one is we can have a realistic roadmaps by setting an achievable delivery commitments. So this is very important when you want to have a very good life cycle or a very good product delivery. 4 different pillars of software maintenance or 4 types of software maintenance. So one is corrective maintenance. So corrective, by the word we can understand that there is some defect in the software and we are supposed to upgrade it by correcting it. Okay, so that kind of a maintenance is called as your corrective maintenance. So there will be a set of defects that is identified by any of the stakeholder, being a client or customer or any end user, where they have enumerated a certain set of defects, and that defects will be taken at priority and it will be provided some solutions. So once you give the solution to a particular software and you have corrected that, we can call that as a corrective maintenance. Okay. So the bugs are normally reported by the user, which is found through testing. So this testing, since it is a maintenance phase, we can assume this testing is done after production. The second type is called as your perfective maintenance. So here by the word we can understand that there is no bug in the software, but there is some performance issues. So say for example some availability issues or reliability issues or any other issues that is hindering the performance. So it is working perfectly, but there is some issues in the non-functional parameters. Okay. So something like usability. So if the end user is not familiar with the UI or any other interface, they can enroll that in your usability, and there could also be some functionality base. If a functionality is a very simple and they want to make it a little bit overwhelmed, we can go for this perfective maintenance. So as the word we can understand that you are trying to increase the performance. The third type is called as your adaptive, wherein you want to change to a particular environment, or say sometimes there could be a change in the operating system, or some regulations may come, or there could be some government initiatives to which the software has to be adapted. So, at that corresponding time we will go for adaptive maintenance. So, reacting to changes in external environments like your OS updates or any new regulations. Fourth one is preventive maintenance. So, preventive is something like you do not want to go into a problem at a later point of time, so you want to refactor. So, what we mean by refactor? Doing some changes in the code such that it is not affecting the rest of the code. So, in order to avoid some future faults, we are trying to do some maintenance, and that is what we call it as your preventive maintenance. So, these are the 4 different types. I will iterate it again. So, corrective maintenance, there will be a set of faults that are identified by the user, and that will be taken at priority and corrective software is delivered. So, that kind of a maintenance is called as your corrective maintenance. The second one is perfective maintenance, where you are trying to establish some performance oriented functionality, say availability or reliability or the response time, whatever. Okay. And third type is called as your adaptive maintenance, where we are trying to adapt to a new environment, say an operating system or any new regulations. Fourth one is the preventive maintenance, wherein we are trying to do something prior to a fault that is forecasted. Okay. So, we are trying to refactor the code to avoid the future faults. So, the next is the types of process models for software maintenance. So, one is immediate response. Immediate response is going to be the quick fix, which is going to be given at a very short time. Immediately you are trying to do some correction and trying to provide that as a software. So, this prioritizes the rapid resolution of issues with minimal documentation, and it is very suitable for urgent fixes. Okay. So, whichever is very important, which is time crucial, those can be taken with respect to your immediate response process model. So, where the immediate functionality is crucial, and though it may lead to long term technical debt. The second is the technical debt accumulation. So, this often is considered when there is a accumulated. So, you have delayed a particular functionality for a long time, and this is a time that you cannot say no. Okay. So, at that particular point of time, all the accumulated technical debt can be given as a quick fix. Okay. But it may not address the entire system fully, but then we are trying to provide that as a functionality. So, over the time this can also increases the maintenance complexity and also the cost. When we give these types of quick fix model, that could create a knowledge silos, that could be a knowledge barrier, because they are not well documented. It is just a quick fix, so that you are trying to deliver at a very small time without any documentation or without any subtle effect in the software. So, this might provide a knowledge silos at the later point of time. So, this is best suitable for throwaway prototypes. So, throwaway prototypes, some things like say which you can throw from the entire project, right. So, it is something like a blueprint. Okay. So, these kind of blueprints can be developed using the quick fix model, but this is not that much suitable, as it may provide knowledge silos and other cost that is being incurred. The second model is iterative enhancement cycle. So, just like our iterative model that we have learned in the process model, this comes under software maintenance. So, the same thing, we have to re-specify, redesign, re-implement and retest. Okay. So same phases like your iterative process model, where you would have the requirement analysis, design, implementation and testing. We now do it again, and so we call that as re-specify, redesign, re-implement and retest. That's all. So we are going to do it incrementally, so that it is going to be a disciplined approach. So each request, the change that is requested will be considered as a micro project, and that micro project will be taken for each and every iteration. So when this iteration goes one by one, you might have developed a very good software at the end. So that is the idea. So basically it is trying to keep the code base coherent, but it definitely requires a disciplined documentation, because it is not necessary to do repeated analysis. The third one is full re-engineering. So full re-engineering is something like you can do it again from the start afresh. Okay. So that kind is called as your forward engineering. So it is trying to rebuild the system using the modern technologies. So you have a legacy software and still it is working, but you want to change the entire design, incorporating the new technologies and new softwares that are available at the right point. Okay. So this will have changes in the architecture, and it may need a very good investment and risk management. Whereas in your reverse engineering, as we have learned in the previous lectures, you would try to move in the reverse direction. So you have the product in hand, from where you will predict what the design could be and what the requirements could be, and then you can find the specific pain points and work from there. So that kind of a engineering is your reverse engineering. Okay, so it is trying to extract the business rules by understanding the existing functionality. So from the functionality you identify the design, and where you identify your business rules from the specifications. So this is exactly very crucial when you try to rebuild something which is existing. The fourth one, the fourth process model is COTS, commercial off the shelf products. Commercial off the shelf products. Okay. So here there could be some products, some set of components that are very well furnished and they will be available commercially. So those products could be taken from the market and we can use those instead of the prior simple functionality that we have. So this sometimes acts as an advantage, sometimes this also acts as a disadvantage. So this is trying to reduce the effort. Why? Because you are not going to do any analysis or design or implementation for that functionality. So the effort with which you want to develop that is reduced. The second point is that if you have any issues at the production, it will be handled by the vendors, not the organization that have used that COTS product. Okay. So the vendors will handle the corrective and the adaptive maintenance for their components. When you have bought that component and you have added that inside your software, everything from that point is within the hands of the vendor from whom you have got that product. Okay. So it is basically like we are trying to free the resources within the organization. So they are not responsible for what is happening with that COTS product. But there is an associated risk. What are they? One is the cost. When they are trying to take the product in their hand, obviously there will be a cost associated, and sometimes there is a possibility of privacy also. You cannot just provide all the details to the vendors. So there could be some license fees and the dependency risk that must be factored into forecast. So when you try to identify a COTS product relevant to the software, and if you are trying to add that to the software, the advantage is that you can do the project in a small time because it is already available. You can integrate that to the software, and from that point on, any feature, any failure, the vendor is only responsible. But there is a associated cost and some risk that have been associated. So those were the 4 different process models. So the immediate delivery, iterative, the third one is full engineering, and the fourth one is COTS. The cost drivers. So the cost drivers that are associated with software maintenance. The first one is internal complexity metrics. With respect to the internal complexity, we are trying to think in the perspective of the code and other features that are available in our hand. So this is going to correlate with the person hours. So how much effort you are going to put in for the development. So when you have a product at hand, okay, and this product may be a legacy product or a new product, okay, there is a person who is going to maintain. So this is the software maintenance people, okay. So this person has to know everything about this corresponding project, correct. So only if the in and out of the entire project is known, this person can do a change, and that might not affect the rest of the functionality in the project. So this is not one single person, that could be a maintenance team, okay. So this understanding becomes the baseline effort that is needed for to understand, and that also is taken with respect to the cost estimation. So first and foremost, the code base size. So how much lines of code or functional points, whichever estimation technique you have, we have to analyze with respect to the project size or the code base size. Code base size is the entire set of project that you have. So if the size is low, is less, obviously the effort that is necessary for understanding that corresponding software is also going to be less, and it obviously increases as and when your size increases. So we also have understood what we mean by cyclometric complexity. So we will draw a graph, and we know the formula, and we have identified that it should be less than 10 or 8, right. So when the size of the code base is very high, obviously it is going to have any problem with respect to the maintenance. Second one is code duplication. So at times people will not follow modularity. So what we mean by modularity, instead of having one single code in hand, it is one basic design principle where you will divide the entire code into small functions, such that one function is very little, say for example 10 to 20 lines of code, and obviously it should be standalone, only then we can call that as a function, okay. So at times when the modularity is not being addressed, there could be a code that is duplicated at many places. When there is duplication, there comes the question of consistency. So when you try to do a maintenance, like when you try to change the software, there is a possibility that the person who is responsible for change would update at one part and may forgot to update at the rest. So this will lead to inconsistency, okay. So duplication of code, if it is very high, maintenance will be very it is tough. The third one is historical defect density. So defect density is number of defects per some lines of code, okay. So, when you have a defect density, if it is reported very high, obviously the maintenance is going to be complex. The fourth one is documentation quality. So, earlier I tried to say you, when you have understood the project fully, then only the maintenance person can do some changes or updations, some type of maintenance, correct. So, how to understand that? Just by reading the code, we cannot understand much rather than going for a documentation. If your quality of documentation is very, very low, it is also a complexity. Okay. So, with respect to the internal complexity metrics, these four are going to be the very highly impacted points. So, one is the code base size. If it is low, your complexity is less, and it gradually increases as and when your code base increase. Second is the duplication level. So, duplication is going to cause inconsistency, and thereby the maintenance might get ruined. And the historical defect density, the number of defects per KLOC, kilo lines of code. So, this is also going to impact. So, all these metrics, if it is going to have a higher value, obviously the complexity of maintenance is very, very high. So, these are the internal complexity metrics. The second one is the external quality metrics. So, these are not within our hand, they are external forces. So, say for example, you have an OS update. So, you have developed the software with one corresponding OS, and if they have given the next version and some functionality is taken. Okay. So, we have many OS versions that they stop maintenance, right. So, when there is an OS update which is unplanned, it is one of the external forces. New legislations. So, the government may give some policies and that may be not aligned with our project. The third one is API deprecations. So, this is one of the significant problem. So, many of the programmers, they tend to use some available libraries through the API or REST or whatever. So, if that corresponding libraries deprecates, the entire software that is going to use that API, through that API, it is going to fail. Okay. So, this API deprecation is a very big problem in new technologies. And user growth spikes. So, this is not much significant, but there could be some changes from the user point of view also. So, this is the external complexity measures that has to be incorporated, that could be foreseen before we go into your software maintenance phase. So, these forces are trying to inject the adaptive work that traditional development centric estimates systematically ignore. The fourth one is the estimation toolkit. So, prior to the software maintenance, there should be a estimation technique with which we have to forecast what could be in future, and we have to correspondingly take some measures when you are in the software development life cycle itself. So, there are several methods. So, here we have listed some 2 or 3. So, here first one is the heuristic ratio method. So, this is one of the top approach which is used in the industry. So, this is trying to provide the sanity check before the maintenance budget. So, what it says is the annual maintenance cost is 15 to 20% of the original development cost. Okay. So, the supplementary models, it also says that it is useful for initial estimates. The heuristic ratio method should be supplemented with more detailed parametric or data driven models. So, we will be learning about the parametric models and the data driven models, more specifically ML related models. So, in the today's world, the machine learning world, we have some models to be used for our identification of these kind of heuristics also. So, parametric algorithms. So, there are many algorithms. So, here we have listed 3 models. The first one is COCOMO, second one is SLIM, which is software lifecycle model, and there is a SEER model. So, this is also an estimation model with respect to the software evaluation and estimation for requirements. So, here this will take the historical data and the project parameters, and it is trying to produce a detailed scenario based cost and effort forecasting. So, these every models are trying to actually provide the forecasting. This may be aligned or may not be. So, this is just an estimation model. Okay. So, COCOMO 2, it is using the size and the complexity, and it is trying size and complexity multipliers for estimating the effort. So, SLIM is a life cycle based. It is as the name says, this is software life cycle management. It is a tool for estimating software life cycle effort, cost and schedule. And the SEER model, it is providing cost distribution and support sensitivity analysis for risk assessment. Okay, so this is another model with which we can identify what could be necessary in future, and based on that we can do some changes in software development itself. This is data driven. So, data driven, the machine learning pictures comes into picture. So, here the version control data, this can provide what we mean by version control. I will say about version first. Okay. So, assume that you are trying to build a software, okay, and you have say 4 modules M1, M2, M3 and M4. So, these 4 modules collectively is going to produce this corresponding software. Okay. So, you have developed all these codes, okay, and you have assume that everything is in version 1. So, I will just name this as M version 1, M version 2, M version 3, M version 4. Maybe I can rename it. I will name it as A, B, C and D. Okay. So, first we have delivered some working software with respect to all the 4 modules, which is A1, B1, C1 and D1. So, put together this is going to be one working software, and I can call this as baseline, because this is the first base model which is working. So, assume that after working this baseline product, and there is some change that is requested with respect to A, okay, and we are trying to do that change and provide A2, which is version 2. So, now in the version 2 will be A2, B1, C1 and D1. So, this together is going to be the working model now. So, now this is the second version. Okay. So, sometimes I can call this as 1.1 if it is a very simple version. So, you will move from a number to another only if it is going to be a major version. Okay. So, from these version changes, we can actually use the machine learning to continuously retrain on new data, and we are trying to adapt to the changes in the team velocity and code complexity. So, when you try to understand how this is going to change, so the second type is the data driven machine learning, where we can use the version control data and provide the insights. So, I will just try to give an example with respect to version control. So, assume that you have a software which is built on 4 different models. So, A, B, C and D. So, these are going to be your modules, and assume that we have completed the entire functionality of all the models, and we have A version 1, B version 1, C version 1 and D version 1. So, I can call this as the baseline just because this is going to work perfectly as the first level software. So, after working this software, if assume that you have a requirement to change and you have changed A and C. Okay. So, now I have changed A and changed C. Okay. B and D is going to be same. So, this is going to be the second version, which is software 1.1. So, this is software 1. Okay. So, you have done a minimal change in the module A and in the module B, and we have the same version with respect to B and D. So, this could be another version. So, by understanding the versions, we can actually understand how the code has changed and how frequently you have committed, so that we can also identify the defect density. So, assume that A is being changed frequently, we can understand there is some defect in that corresponding product and that corresponding module, and we can provide very good intense software maintenance in that corresponding module. So, this is the idea. So, based on the version control data that we have, we can understand how frequently the code has changed, the commit frequency and the defect density. So, by using this, we are trying to forecast the maintenance effort and identifying the high risk areas. So, this is about the version control, and by using the machine learning techniques, we are trying to identify this code changes. So, where all it is trying to, it is having potential maintenance scope. The second one is continuous learning. So, your software might have developed with respect to one data. When you do some changes with respect to new data and adapting some new changes in the velocity, everything, how it is going to react. So, based on that machine learning technique also, we can forecast or estimate the accuracy and estimate where actually your software maintenance can come in. The last one is ensemble learning. So, ensemble learning is a very famous learning in machine learning perspective. So, what exactly we do is there could be several algorithms that is trained in parallel or in sequential, and we will try to use those models and estimate the accuracy. We are trying to predict the accuracy. So, it combines multiple models and to improve the prediction accuracy. This approach leverages diverse data sources and algorithms and provides robust maintenance forecasting. So, with respect to budget, we have to make sure the entire data that we have is understood. So, feed all the model outputs into sprint planning and allocate the buffers. So, we have to identify all the pain points and we have to allocate them, track them and compare, and if we want, we can also recalibrate if there is any errors. So, as a summary, we first learned what exactly is maintenance and where it fits in the software development life cycle, and we have learned the process models. So, we have learned 4 different process models. One is immediate, and second is incremental, third one is full engineering, and fourth one is COTS. And we have understand that immediate is not that much good because we are just trying to give it as a immediate fixture. It may not close the entire problems, and incremental is a very good approach. When you go for multiple increments at a good fashion, you can provide a very good maintenance with respect to this process model. Full engineering is not that much claimable because you are going to redo the entire phase, and use of COTS, we have understood what is the advantages and disadvantages, and we have learnt about the cost drivers, implicit and the external, both we have learned, and the cost toolkit, that is estimation for identifying the maintenance pain points and how the budgets are being taken. Thank you.